Hello everyone, this is our science teacher Tim Martin, and in this astronomy video I want to talk about the Sun, our closest star. If you recall, back in the unit about the solar system, we discussed that the solar system was formed from a large gas cloud called a nebula. The nebula gradually coalesced due to the forces of gravity. Over 99% of the material in the nebula went on to become the Sun, our central star. The remaining bits of debris gradually coalesced and collided together to form planetesimals. The planetesimals accreted to form larger protoplanets, and the protoplanets eventually became the planets that we know of today. Distance from the Sun determined the composition of the planets. We talk about this as differentiation. The inner planets are warmer, they have heavy elements, and are generally rocky. The outer planets are significantly colder, and they're composed of the lighter elements and ices. But let's take a look at the central object, the Sun. Here we see a diagram of a Sun, but let's cut away and see what's going on the inside. We can see in this animation that there are a number of different layers to the Sun. Let's look at them individually. Starting out with the core, where we find temperatures of over 15 million Kelvin. It is the core that holds the energy source of the Sun, where hydrogen fusion is occurring. Hydrogen is fusing into helium. We know this takes temperatures of at least 10 million Kelvin. We see hydrogen atoms or protons gradually colliding together, forming heavier atomic nuclei. Keep in mind, it was Albert Einstein who came up with the famous equation E=mc², describing the proportional relationship between energy and mass. In the process of nuclear fusion, energy is created when mass is lost during the fusion reaction. When people realize that the Sun is undergoing nuclear reactions, a common question is, why doesn't the Sun blow up? Others ask, when will the Sun blow up? This question is actually kind of interesting because it sort of misses the point. You see, energy is released through thermonuclear reactions. The Sun is blowing up. That's what stars do. So maybe a better question is, why doesn't the Sun blow itself apart into small pieces? Well, at the same time, the Sun is 300,000 times more massive than Earth. The immense forces of gravity are trying to crush it. So we see a balance between the outward pressure from the thermonuclear reactions and the inward pressure by gravity. We know now that the Sun is composed of approximately 92% hydrogen. We expect that the Sun is halfway through its lifespan. It is approximately 5 billion years old. Beyond the core, we'll find the radiative zone. Here temperatures range from 7 million down to around 2 million Kelvin. Out from the radiative zone, we find areas of rising and sinking gases. This is the area that's known as the convective zone. It is in these areas, the radiative zone and convective zone, where we find the source for the Sun's very strong magnetic field. In this NASA animation, the blue lines represents the Sun's magnetic field. Due to the odd rotation, the magnetic field lines overlap and become very twisted. On from the Sun's magnetic field, let's go out towards the surface. The visible surface of the Sun is known as the photosphere. Here we find temperatures of approximately 6,000 Kelvin. It's on the photosphere that we may find sunspots, much cooler areas on the surface of the Sun. As we see through this telescopic image, sunspots can be quite large across the surface of the Sun. So what are sunspots? They're disruptions in the magnetic field. The disruptions of the magnetic field slow down the convection. When the convection is slower, the surface becomes cooler and therefore less bright. We've mapped and monitored sunspots over the years, and it turns out there are cycles of sunspots with a rise and fall approximately every 11 years. Here again is another image that I took through a small telescope showing the number of sunspots near the solar maximum back in 2014. Sunspots, like I said, can be quite large. Here's an image showing the Earth for scale. Several of these sunspots are much larger than our entire planet. We can use sunspots to track the rotation of the Sun. As mentioned earlier, the sun has a bit of an odd rotation. We can track sunspots across the equator, and they revolve around the sun every 25 days. However, sunspots near the poles may take 33 days to make a trip around the sun. This large ball of gases and plasma does not have a uniform rotation like a solid planet. This image from the National Optical Astronomy Observatory shows a sunspot with granulation around it. The whiter or brighter areas are areas where there's hot gases welling up from deeper inside the sun. These areas are much hotter, and you can see the depression of the cooler sunspot. Flares or eruptions of charged particles are often associated with sunspots. If the sunspot is inhibiting convection, it may make sense that significant energy may build below the sunspot and erupt violently as a solar flare. The sun was in a particularly active phase back in October of 2003. We can see several active regions by the bright spots on these images captured by a solar orbiting observatory. As the active regions face closer to the center of the screen, there was a solar flare. Out from the photosphere, we find the next layer, the chromosphere. We'll notice that temperatures are rising once again. It's in the chromosphere that we may find prominences. Prominences may occasionally be visible, such as this pink area on the limb of the sun that I photographed during the 2017 solar eclipse. Using specialized solar filters, such as a hydrogen alpha filter, I was able to photograph these prominences also in 2017. Here you can see these large glowing clouds of gas reaching up above the edge of the sun. Of course, my pictures pale compared to some of the NASA satellite images. Images taken from the Solar Dynamic Observatory can be quite impressive. These large looping clouds of plasma extending along magnetic field lines of the sun. Finally, we get out to the corona, or the sun's outer atmosphere. Here, temperatures may go back up, exceeding more than 1,000,000 Kelvin. Of course, the corona, or the crown of the sun, is very spectacular in a solar eclipse. Here we see the sun's corona during the solar eclipse of 2017. We may also see the corona with specialized instruments aboard orbiting satellites. Here we see an image from the SOHO satellite where an artificial eclipse is made by blocking out the central sun. In this brief video, also from the active time back in October of 2003, we can see numerous coronal mass ejections as particles are streaming away from the sun. This video also includes a distinctive particle shower from the massive solar flare. Those high energetic particles flooded the solar cameras. Lastly, we may talk about the aurora borealis or aurora australis. When charged particles erupting from the sun interact with the Earth's magnetosphere and atmosphere, they can cause the beautiful northern and southern lights. This image was taken when I was on expedition to Lake Elgagikhan in northern Siberia. I stood out at night and watched the lights from the solar storm dance above the Earth's magnetic field until my camera froze. Of course, now we know through studies from the Hubble Space Telescope and other instruments that there are auroras reaching further out into the solar system. We know that the solar wind extends past all the planets until it interacts with the solar wind from other stars. Thanks for watching, and I hope to see you again on another Earth Science video.